So today we present my PhD thesis, Learning Pattern-Based Relation Extraction from Natural Language on Knowledge Graph. Before to introduce my topic, I need to discuss what is DBpedia. So DBpedia, quickly, that's where I started my work here at INRIA. That is an open general purpose knowledge graph built on the top of Wikipedia. But DBpedia results from the extraction of data, mainly coming from the info box that you can see at the top right of each Wikipedia articles. However, these info boxes capture only a small fraction of the knowledge contained in the Wikipedia pages. And most of this information is locked into unstructured text of Wikipedia, motivating our main research question. How can we learn effective, customized extractors that target...
Excusez-moi, mais là, moi, j'ai des gros problèmes de son. Alors, je ne sais pas si tous les gens à distance ont aussi des gros problèmes de son, mais moi, j'entends presque rien. J'entendais très bien tout à l'heure, et là, je sais pas...
Ok, là c'est mieux?
Oui, là c'est mieux.
Ok.
Merci.
To address this research, we adopted an iterative strategy. And our first step was to understand what was the current state of art related to relation extraction. So relation extraction is the task related to extracting a graph from a text. And when we propose evaluating, thanks to their first work, we addressed in a second step to find what was the best task formulation what was the best task formulation to extract relation only focusing on data types properties. The third research question we addressed was related to how to systematize this pattern-based extraction from a dual base integrating human in the loop. And the last research question we addressed was related to the extension of our work to both type of properties, so namely the data type and the object properties. So let's start now with the first research question, which is related to how to survey or understand the current state of art of relation extraction. So this first work was published in ACM Computing Survey, and it is still under review today. So when I started to, when I was faced to my topic, I first began my research by conducting a systematic literature review. And a systematic literature review is a methodical and rigorous process for identifying, assessing, and analyzing the primary studies already published related to a given research question. So as my research question was is related to relation extraction, the first thing that I did was to search in Google Scholars these keywords, relation extraction. And I obtained from this search more than 4 million articles. On screening such a volume is completely impossible. So for this reason, but I have to say also that it's not specific to my context. A recent study estimates that the research volume grew from 47% between 2016 and 2022, motivating us to develop a software that is called Silex, and that allows to support each step of a systematic review. In our context, in my context, I propose to focus on 3 types of articles: the survey already published related to relation extraction, the data sets already published too, and the models that propose to solve this task. And Silex helps us to support each step of this systematic literature review, from the from several digital libraries of the articles to the annotation of these articles, and finally Silex help us also to obtain a first layer of annotations coming from a paper with code. And the resulting data set was the backbone of the survey we wrote about relation extraction. And as this survey is titled a systematic review from the emergence of transformers, I will spend a bit of time to explain what is transformers. So you have several architectures that you can use to solve a relation extraction task. And you can see on this graph that before 2022, the architecture used by the researcher to solve this task was much more diverse than after 2022, where almost all the research proposed to use the transformer architecture to solve the relation extraction task. So what is concretely a transformer? So the transformer is an architecture that you can use in different ways to obtain a pre-trained language models that could be used and adapted to solve a different NLP task. So you can use only the encoder models. This is this block that you can see here, and it allows us so the encoder models allows to obtain text vectorial representation that transform a sequence of text on something that is more close to vectors of numbers that could be used for classification. You can also use the decoder part of the transformers, and this is the case. This part of the architecture allows to obtain, to generate a sequence of text given an initial input. And this is the specific architecture that is used in GPT, and it's shown when scaled to be really effective. So that is this architecture that you know, that you can know finally when we talk about large language models. And finally, you can use both blocks together. So this is the encoder-decoder architecture, and this is on the main known models. In this case, are BART and T5. So, okay, so as you know more about the different type of sub-architecture related to the transformer, let's show how they are used by the researcher since 2019. So as you can see, in the first stage, before 2022, the encoder was the main were the main models that were used by the researcher to solve the relation extraction task. But since 2022, the landscape changed a bit. As you can see on that chart, so the decoder and the encoder-decoder models became now the favorite architecture to solve the relation extraction task. And it demonstrates and it indicates here a concrete shift in the methodology used by the researcher to solve the task. With the encoder models, generally the researchers were obliged to work iteratively by first trying to find the named entity in the text, then trying to identify which relation were expressed by the text to finally obtain a relational graph. With generative models, we researchers are now able to solve the task in an end-to-end manner, from a text to a graph, directly. So, thanks to this work we conducted, we had also the occasion to underline 3 gaps in the literature. So first, the existing model do not generate LGF relation directly. Secondly, the dataset proposed were mainly built from the combination of Wikipedia and the knowledge graph, but many of them express the object as untyped strings losing semantic grounding. And finally, very few methods target a specific part of an ontology. So, as we had now a concrete understanding of the state of art, we propose, with our second research question on our second work, to first formalize how to conduct relation extraction a bit differently, but we also had to know how to formulate this task. And we focused on, in this work only on the data types properties. This work was the lead to two different publications. The first one at ESWC, and the next section of this work was proposed at Semantic Web Journal. So, okay. I told you about relation extraction, but in our case, we propose to reformulate or to propose a new task, which is called the RDF pattern-based extraction. So you have a Wikipedia article, and we propose to use a shackle shape that defines which relation we want to focus on. On this shackle shape also detail which properties is mandatory or optional. And in this context, we also propose to use small language models that could fit to really knowledge-intensive context. And these kind of models will be fine-tuned, so adapted to produce a relational graph. So why to use a small encoder-decoder rather than a large language model like ChatGPT? For several reasons that came from our understanding of this state of art. So first, they are cheaper to fine-tune and faster in inference. Secondly, they are better dealt with context input and they produce fewer hallucinations. And finally, they are easier to audit and they allow data sovereignty. So, okay, we have a concrete new task and a new process, and we also propose to use now our shackle shapes to validate all the graphs that will be generated by our model. Okay, and our first step was to focus only on the person expressed by DBpedia. So our shackle shape here is focusing on the person and is also targeting 7 properties. Some of these are mandatory, have the birth date, the birth year, and the label, and some of these, the others, are optional. The death date, the birth year, the birth name, and the alias. I forgot to mention the fact that data types properties are related to strings, values, and dates. And this shape, even if it's only focusing on 7 properties, is already focusing on 1/6 of DBpedia. So, okay, you know now on which shackle shape we want to focus on. Now, the big question of this work was to find and to determine which decoder to use to fine-tune and extract models, and how to write our graph as a sequence of text. So you have now a large overview of our experimental setup. We first started with DBpedia by sampling 5,000 examples from DBpedia. As previous experiments shown us that it could be enough to fine-tune a model extracting the person and the properties that I just presented you. We then translate all the graph through 16 syntaxes that I represent you now. So, the 2 first syntaxes are related to a list and a tag, and both of them are represented the graph I was talking about, I was telling you. So they are the 2 main used syntaxes to extract a graph from a text. Aside from it, as our work is grounded to, is related to semantic web, we also compare and benchmark 4 syntaxes, the 4 main syntaxes of the W3C. So namely RDF XML, which is the historical syntax, but also Turtle, which is a more human-readable and more compact syntax, but also N-triple, which is a line-based syntax, and more oriented to be on more machine-readable, let's say. And finally, JSON-LD, which is in line with the modern use of JSON in the web application. Okay, we also propose a new syntax called Turtlelite, which is meeting the prefix declaration that you can see at the left. But it is, this syntax is also omitting the prefix declaration before the entities and the predicates. Aside from that, we also propose several for variation. And the first one was only focusing on targeting turtle light. And in this case, we propose to write it only on one line. We also propose, as Turtle is integrating factorization process, we also propose to unfactorize the Turtle triples. And we propose, in the case of on the list and the tag syntax, to factorize both of these syntaxes. And finally, to reduce the complexity once again of Turtle, we propose a Turtle ultralight syntax, which is now omitting the column character that you can find before the entity and the predicates. So, as we also wanted to evaluate and prevent the potential overfitting, we propose to conduct all our experiments. It will be the case during all the different models. It will be the case to all the models that I will talk about in the next slides. We cross-validate each models to be sure that we are not overfitting. Okay, so we use 5,000 examples for the fine-tuning, 1,000 for the testing at the end of the experiment, and 215 fixed examples used during the validation through the fine-tuning. So about the fine-tuning, that comes to the models. So we benchmark here 5 encoder-decoder models, namely BART T5, PAL T5, FLAN T5, and CODE T5, that represent an interesting overview of the different of these encoder-decoder models, since they are all pre-trained differently. They all use different training set, and they are representing differently the sequence of text using different tokenization strategies. And to benefit to the limited context of each model, we also added the specific syntax token to the model's vocabulary. And in the case of JSON-LD, which is a really verbose syntax, we added 46 tokens. And now, let's talk about the evaluation. So how we compare our model. We use naturally the F1 metrics computed at the macro and micro level. And we also propose 3 new metrics, which have the rate of parts triples. How many graphs are we able to understand at the end of each generation? The rate of right choice for describing the subject, and finally the rate of graph validating the shaker shape. But we understand from our experiments that fine-tuning doesn't mean well writing graph at the end. Here you have an example, for example, of a graph. This is a graph, but it is completely malformed at the end of a sequence, and we can't, on the computer couldn't read this graph. And it was the case, particularly of T5, of PAL T5 and FLAN T5, that were not able at all to produce any RDF syntaxes. In the case of CODE T5, it was able to produce some of them, and we showed during our experiments that it could be also used to repair some graphs. So let's now talk about our challengers, which are T5 and BART. So here on this graph, you have on the x-axis the performances of the graph of all our different configuration, and in y-axis the training time they needed to be fine-tuned. And we can find on this graph 3 interesting configurations. So here you have T5 using JSON, which is really performant, but also really costly to train. Aside from that, below all this configuration, we can find 2 specific syntax. So BART with using the tag syntax, and BART plus Turtle Lite. Both of them seems really cost efficient to train, and lead to really good performance too. But in our case, we prefer to use Turtlelight as it is closer to the RDF specifications. Okay, so that's normally the time to conclude this second part. So thanks to our experiments, we've shown that the shows of the models on the output syntax are essential. We show that for obtaining performing models with T5 on JSON, we needed more than 100 minutes of fine-tunings, where we just needed 10 minutes of fine-tuning using BART on Turtlelight. Aside from it, the BART or Turtlelight configuration allows to obtain RDF outputs that are always possible, that are always choosing the right subject array, and finally, the graph produced are always validating the shaker shape. So now, let's discuss, as we have like base ground on, as we now have syntax on a model to use, we are now focusing on how can we systematize this task using a dual knowledge base on some human feedback. So this work was published at ISWC last year, this year. In my last, two slides ago, I told you that our method allows to obtain RDF output, always validating the shaker shape. But training a model on search statements may promote hallucination in text that does not convey a mandatory property. If we oblige our model to extract the complete shape, we can oblige the models in a way to generate predicates where no information are expressed by the text. So, okay, at this moment, we propose to reformulate the task. So, the initial shaker shape is now called the maximal shape. We also select training example containing at least one property of a maximal shape. And finally, we compare now the list of a property generated with an expected rather than using the shackle validation at the end of the process. With that in mind, let's talk now about casters, which is a software and a framework that we propose. On this software is composed of two steps. The first step is to initialize a knowledge base using DBpedia and Wikipedia. And the second stage is about the knowledge distillation. So the knowledge distillation process starts by defining a maximal shape. So our maximal shape here, in this case, we continue to use the DBO person shaker shape I told you about a few slides ago. The next step is now the rule augmentation. As DBpedia has several coverage issues, we propose, in our case, to fill in the blanks by defining some rules. And here, we saw, by analyzing our knowledge base, we saw that many years were missing. And for this reason, we propose a rule that infers from the dates the missing years. And all these new trippers are materialized using a Sparkle contract. And the last step of this process is called the wiki check. This is a process that is verifying and answering that each values from the graph are expressed by the text. So we use string matching for the strings and the date finder Python library to check the dates. And at the end, we obtain a distilled knowledge graph. So let's now talk about the second part of this framework, casters, which is related to the light active learning process. And this is about process that integrates a human in the loop. So the light active learning process is starting by sampling a set of examples from our distilled knowledge base to fine-tune a first model. The second step is about sampling two sets of text and graph to test our model, which will lead to the production of two error sets. and the set will be then evaluated by an annotator. So you have two kinds of errors. You have the first type that is the false positives, where the model generates triples that were not expected by our testing set. And in this case, the annotators will have to correct the data set by adding, if they are expressed in the text, the false positive into our corrected set. The second type of errors are related to false negatives. That is errors, there are errors that are expected by our testing set, but not generated by our model. In this case, the annotators will have to delete these errors from the corrected data set if they are not expressed by the text. Okay, we have now two corrected data sets. They are named D2 plus and D3 plus. And this data set, well, the first data set, corrected data set, will be used to fine-tune a God model. And finally, as we wanted to also compare our approach with the first task design, we fine-tune another model using using now training example that validates each time the maximal shape. We use now our last corrected data set to compare all our models. And as we wanted also to evaluate in a knowledge completion perspective how are our models able to generate triples that could be interesting, triples that were not covered by our knowledge base, we also propose, and we ask our annotators to once again validate the different errors that were produced during the evaluation of these three last models. We also propose to measure that, that is called the discovery rate. So that is about all the, that's computed by, as the ratio of all the relevant facts on all the errors. So, in this table, you have the results of the evaluation of conducted on D3+. And here we can see, regarding of the F1 metrics, that the task design largely improved the performance of the models, mainly by avoiding hallucination. And regarding now our discovery rate, we can see that using a model trained on a corrected set helps to discover new relevant facts. So, this is now the moment to conclude our third part of our presentation. We show that castles allows to build pattern extractors in synergy with the knowledge graph. We also demonstrate that the new task design allows to reduce the hallucinations. And finally, the human annotations help to complete the knowledge graph with relevant facts. So let's now try to cover all types of properties. We only, for the moment, focused on data types properties. That's the moment also to extract object properties, which led to our third research question. This third work was presented last week, in KCAM. And when we came to address this research question, it naturally opens up a broader challenge. How can we generalize pattern-based relation extraction over underrepresented properties? So, let's start first by extending the shape. We were focusing before it only on data types properties. We will now add in our shackle shapes 3 new object properties: the nationality of a person, the birthplace, the death place of this person. As the next step of the distillation process I just presented you is about the augmentation using rules, we will also add some rules related to, and focusing only on object properties. And these rules are augmenting the knowledge at the country level. So here, if we are missing the country of the death place of person, we infer it from the city of the death place. And finally, as our last step was about the wiki check, we are now using the markdown version of the article to be able to verify if the URI of related to the object are convey the graph properties we have in our graph. So we delete here all the object properties that are not referred into the text. Okay, so now we have all the elements that enables us to obtain a sample from our distilled knowledge base. And in this experimental setup, we propose first to select graph that contains at least one object property and one data type property to be able later to separate the shape into different subsets. And we also propose to sample articles, Wikipedia articles that contains articles created only before the pre-training date of the BART model we use, namely 2021. So in this context, we fine-tune 6 models. So the first 3 models are focusing on using the markdown abstract of the Wikipedia article as input, and the 3 others use the plain abstract. Aside from it, we use also in the first case a shape only containing the data type properties. In the second setup, we use a shape containing only the object properties, and in the last case, we use a shape that is containing all the properties we focus on. And once again, we use a 10x fold validation to conduct our experiments. Our results are pretty good. We obtain strong performance across all the models. It seems easier to extract the data type property. And this statement holds for both type of input, the markdown one and the plain text one. As we wanted also to compare ourselves with other models, we use Rebel, which remains a strong state of art today, to compare the performance of our model with this model. And as Rebel isn't able to extract all the properties we are focusing on with our complete shape, we now propose a subset of this shape, focusing only on the properties that can extract Rebel. And here the results are pretty clear. We are better than Rebel by 20 micro F1 point and 30 F1 point. We obtain these results by being 4 times smaller, by requiring only 10 minutes of fine-tuning, and by producing LDF trippers directly, without post-processing. But until here, I didn't discuss a critical observation related to the high variance that we can see across our metrics. By comparing the F1 macro and micro, we can hypothesize that it comes from something related to our underrepresented properties. And to validate this hypothesis, we first now divide our complete shape into 2 new subsets. The first one is related to a subset containing only the frequent properties. And the second subset is containing only the rare properties. And we train now models on both type subsets of the shape. On here, the results are also pretty impressive. As we can see, we can see here that the rare properties are completely drive variance. So the problem is coming from the underrepresented properties. So how can we solve that? 2 strategies were undertook. We first proposed to follow classical machine learning strategies to tackle this issue, and we also propose another set of strategies that are related to the sufficient exposure, I will define it later. So the first set of strategies have so you can see here the first set of strategies. We use here our initial configuration in gray, and we compare it to different new strategies. First, we propose to oversample the raw data for fine-tuning a new model. Secondly, we also propose to scale by factors of 2, 4, and 10s the training set. We also propose a stratification strategy that oblige to keep the same distribution between the test set and the train set. And finally, we also propose a weighted loss strategy to oblige our models to take more attention to the rare property. And to compare these models, we use different test sets. The first one is oversampling and is containing more common properties. The second set is containing more rare properties. The third one is a random sample. And the last one is containing now only articles that were published after the BART pre-training. And from these results, we do not observe significant improvements. But one positive outcomes could be underlined. We are able to generalize our extraction on new Wikipedia articles, which is a good thing. So, as we don't have any solution and we didn't solve our problem related to rare property, we turn now to a more recent theoretical insight that was proposed by Alan Su, and that at ISER 2025. And during this tutorial, Alan Su told us that the language models needs to be exposed to a fact at least 1,000 times to be efficiently retained by the model. So in our case, we can maybe ask this question. Does the language models need to be exposed to a property at least 1,000 times during the fine-tuning to be able to extract its property? So as we can see, when we observe and analyze our base configuration training set, we see here that the alias property fall below the sufficient exposure. And the first strategy we propose is simply to add all the alias properties we have in our knowledge base into the training set. The two second strategies are based on naive synthetic data augmentation. And we, thanks to this strategy, we are able to reach these 1,000 exposure thresholds. And finally, in our last strategy, we propose to iteratively sample each property to reach this threshold for each of these. And the results are now analyzed given two test sets. The first one is a random set, and the second one is a corrected data set that is corrected in the same way than the the proposal we did in our last works. And this data set is corrected by asking to an annotator to correct each relevant and to add each relevant false positive into the test set. And we see here that only our last proposal is able to solve, enables to solve effectively the extraction of the relation, even the rare ones. And to verify it, I propose also to analyze now the F1 metrics focusing on each property, right? So here you have the result given by property, and you can see here on the right side on the decorrected data set that only our last configuration is able to extract all the rare property. So, okay. From our last works, we demonstrated that it is possible to extract both types of properties. We also saw that BART pre-training data were not memorized. we saw that castles can compete with Rebel, and we also saw that it is essential to take care of the exposition, not only of the rare property, but also of all property to extract them, to extract all of them effectively. Let me now talk about a result that didn't, some preliminary experiments that wasn't published for a moment. This is related to the text-to-kg bench, and this benchmark is proposing to evaluate relation extraction given 19 DBpedia classes. And to be able to compare ourselves with this benchmark, we first distill a knowledge graph for each class that you can see on the screen. We then fine-tune a model for each of these classes to have at the end one specialized model per classes. And the results we obtain are pretty good when we compare ourselves using a Wikipedia test set. But we can see that we have also really high variance that could be related to a problem we tried to solve and we solved in the last work I presented. And when we compare ourselves with a WebNLG test set, we can see that our models perform better than the baseline proposed by the benchmark. So, this is the moment for me to conclude. First, we saw with our first proposal, and we propose with our first proposal a comprehensive survey offering a detailed overview of the field. And we also proposed by the same occasion a software called SALLEX that is actually used by some of my colleagues to start their research. Secondly, we also demonstrated we also proposed the foundation of our pattern-based relation extraction by demonstrating that turtle lights combined with BERT enabled efficient and resource-friendly relation extraction. In our third works, we propose to systematize this process with the frameworks, castles, that enables to extract to fine-tune relation extraction models using human feedback. And finally, we demonstrated that our models are able to generalize over different types of properties, and we also propose a solution for extracting shape containing rare property. So all our works conducted to the publication of the open publication of all our software, all our data sets, the different model that I just told you, the 16.1, related to the text-to-kg bench are already available on GingFace. And that's now the moment to draw some perspective that emerge from this PhD. First one, as we need shackle shape to feed our models, it may be interesting to develop some tools that could propose and design shapes in combination of large language models and knowledge graph. And this is something we already started by working in collaboration with the King's College London. Secondly, we saw that it could be interesting to develop augmenting strategy to augment the rare properties shape. But we also saw that we can obtain a lot of different, we already prepared and fine-tuned different experts using the Casters framework, so it could be really interesting to combine and to use all of them using maybe higher level frameworks, maybe using a mixture of experts or integrating them into an agent-based system. And finally, it could be really interesting to compare our methods and to apply our methods to other kind of inputs, but also other kind of knowledge base. Thank you.